Interstellar object 3I Atlas is now displaying more than 7 tightly collimated jets streaming out from its nucleus, with some extending 1 million kilometers toward the Sun. These dramatic new images mark another unexpected turn for this object, which has cycled through displaying an anti-tail, then a tail, then no tail, and now multiple jets in what appears to be a breakup event or something else entirely. Harvard astronomer Avi Loeb has calculated that if these jets are natural sublimation from pockets of ice, they would need to carry approximately 5 billion tons of material. This massive amount of ejected material presents a puzzle that challenges our understanding of what we're observing. For carbon dioxide ice, which requires the least energy to sublimate compared to water ice, producing jets of this scale would require a surface area equivalent to an object 20 kilometers in diameter. This calculation creates an immediate problem for understanding 3I Atlas. The Hubble Space Telescope captured images of the object back in July that indicated a much smaller nucleus than what would be needed to produce these jets. The surface area required to generate the observed jets through natural processes significantly exceeds what astronomers estimated for the actual size of this interstellar visitor based on those earlier observations. The discrepancy between the required surface area and the observed nucleus size forces consideration of alternative explanations. If the object maintains the size estimated from the Hubble images, then the conventional model of cometary outgassing cannot easily account for the mass being ejected in these jets. This mismatch between theory and observation has prompted examination of multiple scenarios that might explain the dramatic activity we're witnessing. The timeline of observations shows how rapidly 3I Atlas has transformed. Just last week, images showed the object with no tail at all, appearing as a simple point of light against the stars. Before that, observers documented a conventional tail pointing away from the Sun, the type typically seen in active comets. Earlier still, the object displayed an anti-tail feature, which occurs when viewing geometry allows us to see larger dust particles trailing behind in the object's orbital path. Now we observe multiple jets extending in various directions, some reaching extraordinary distances despite pushing against the solar wind. Loeb presents 2 interpretations of this data, though neither is confirmed at this time. The first hypothesis suggests the object has broken into pieces, possibly due to thermal stress or tidal forces during its close approach to the Sun. If 3I Atlas has fragmented, the combined surface area of tens or possibly hundreds of fragments could provide enough ice-covered surface to generate the observed jets through natural sublimation. The tidal forces from the Sun would gradually separate these pieces over the coming weeks, making them individually detectable as they drift apart. The fragmentation scenario would explain how an object initially estimated to be much smaller than 20 kilometers could produce jets requiring that much surface area. When a comet or asteroid breaks apart, the fresh surfaces exposed to solar radiation can become active sites of volatile sublimation. Each fragment would contribute its own outgassing, and the combined effect could account for the massive amount of material being ejected. The Sun's tidal forces would then pull these fragments apart at rates determined by their individual masses and positions relative to the main body. The second hypothesis considers technological thrusters as the source of the jets. Rockets typically eject gas at speeds 10 times faster than natural volatile sublimation from a comet's surface. Ion thrusters, which use electromagnetic fields to accelerate charged particles, can achieve speeds up to 100 times faster than natural ice pockets would produce. If the jets are technological, they would carry much less mass while maintaining much higher velocities, and the object would maintain its structural integrity rather than breaking apart into fragments. These two scenarios make testable predictions that observations over the coming weeks can verify. Natural fragmentation would produce slow-moving jets carrying large amounts of mass, with visible separation of fragments becoming apparent as tidal forces pull them apart. The fragments would follow slightly different trajectories based on their masses and the varying solar radiation pressure each piece experiences. Technological thrusters would generate fast jets with minimal material, while the object remains intact as it continues its trajectory through the solar system. The distinction between natural sublimation speeds and artificial propulsion speeds provides a diagnostic tool for determining the jet's origin. Natural volatiles sublimating from a comet's surface have characteristic ejection speeds determined by the temperature at the object's distance from the Sun. These speeds are well understood from decades of comet observations and laboratory experiments. Any significant deviation from these expected speeds would require explanation beyond conventional cometary physics. Temperature plays a crucial role in determining natural sublimation rates. At 3I Atlas's current distance from the Sun, the equilibrium temperature of a dark surface would allow carbon dioxide ice to sublimate readily, while water ice would remain mostly frozen. The thermal energy available from solar heating sets an upper limit on how fast molecules can escape from the surface. This physical constraint means that natural sublimation produces predictable ejection velocities that depend primarily on the molecular weight of the escaping gas and the surface temperature. The solar wind plays a crucial role in shaping these jets and determining their observable characteristics. The solar wind consists of charged particles streaming outward from the Sun at speeds of several hundred kilometers per second, varying in density and velocity with solar activity. Knowing the properties of the solar wind, including its speed and density at 3I Atlas's current position, allows astronomers to calculate how much mass the jets must contain to extend 1 million kilometers while pushing against this particle stream. The jets pointing toward the Sun face the strongest solar wind pressure, making their extent particularly diagnostic of their composition and ejection velocity. For these sunward-pointing jets to reach 1 million kilometers against the solar wind requires either enormous amounts of slowly moving material or smaller amounts of very fast-moving particles. The relationship between jet extent, solar wind pressure, and ejected mass provides another constraint on the possible mechanisms producing these features. The interaction between the jets and the solar wind creates complex structures visible in the images. As ejected material encounters the solar wind, it gets swept back and shaped by the magnetic fields carried in the solar plasma. This interaction can create the appearance of multiple tails or fan-shaped structures, depending on the viewing angle and the relative velocities involved. Understanding these interactions requires sophisticated modeling that accounts for plasma physics, magnetic fields, and the motion of charged particles. December 19th marks the anticipated date for obtaining the clearest images of 3I Atlas as it continues its approach. The improved viewing geometry on this date will allow telescopes to capture higher resolution images that could reveal whether the object has fragmented or remains intact. The alignment between Earth, the Sun, and 3I Atlas on this date will provide optimal illumination and viewing angles for detecting small fragments if they exist. However, new imagery arrives daily from both ground-based telescopes and space observatories, each potentially revealing new details about the object's structure and behavior before that optimal viewing date. The rapid changes in 3I Atlas's appearance have been remarkable and unlike typical cometary behavior. The object initially displayed an anti-tail feature pointing away from its direction, of motion, a phenomenon that occurs when Earth crosses the orbital plane of a comet and we observe larger dust particles left behind in the comet's orbit. Then it developed a conventional tail pointing away from the Sun as solar radiation pressure pushes small dust particles outward. Subsequently, it appeared with no visible tail at all in images from last week, before now showing these multiple jet formations extending in various directions. This sequence of transformations differs from typical comet behavior patterns observed over decades of monitoring solar system comets. Most comets show gradual changes in activity levels as they approach and recede from the Sun, with predictable variations in tail structure based on viewing geometry and solar distance. The rapid and dramatic shifts in 3I Atlas's appearance suggest either unusual composition, structure, or possibly non-natural mechanisms at work. The energy requirements for producing these jets through natural ice sublimation are substantial and worth examining in detail. The calculation specifically considers carbon dioxide ice because it requires the least energy input among common cometary volatiles. Carbon dioxide sublimates at -78.5 degrees Celsius under standard pressure, though the near-vacuum conditions in space allow sublimation at even lower temperatures. Water ice would require even more energy and therefore an even larger surface area to produce jets of the observed scale, making it an even less likely candidate for explaining the observations. The 5 billion tons of material that would need to be carried in these jets represents an enormous mass loss for any celestial object. For comparison, typical comets lose millions to billions of tons during close solar passages, but this occurs over weeks or months, not in discrete jet events. The concentration of such massive material ejection into distinct jets, rather than diffuse outgassing patterns, adds another layer of mystery to 3I Atlas's behavior. To put 5 billion tons in perspective, this mass equals roughly 5 cubic kilometers of water or about 2 cubic kilometers of rock, depending on density. For an object to lose this much material in jets while maintaining structural integrity challenges our understanding of how cometary bodies behave. Most comets that experience such massive outbursts either fragment completely or show clear signs of major structural disruption, visible in subsequent observations. If fragmentation has occurred, the coming weeks should reveal the individual pieces as they separate under the influence of various forces. The Sun's tidal forces would pull these fragments apart at predictable rates based on their masses and the object's orbital parameters. Additionally, solar radiation pressure would affect smaller fragments more strongly than larger ones, causing differential acceleration that would spread the debris along the orbital path. The absence of clearly resolved fragments in current images doesn't rule out recent breakup, as initial separation might be too small to detect with current telescope resolution. The possibility of observing a real-time fragmentation event makes 3I Atlas particularly valuable for understanding how interstellar objects respond to the stresses of close solar approach. Previous observations of fragmenting comets within our solar system have revealed that breakup can occur through various mechanisms, including thermal stress from uneven heating, pressure from volatile pockets exploding, or tidal disruption when objects venture too close to massive bodies. Thermal stress represents a particularly relevant mechanism for 3I Atlas. As an object that has spent potentially millions or billions of years in the cold of interstellar space, sudden heating during solar approach could create extreme temperature gradients. These gradients generate mechanical stress as different parts of the object expand at different rates. If the object contains a mixture of materials with different thermal properties, this differential expansion could literally tear it apart. Loeb emphasizes that science requires following the evidence wherever it leads, regardless of preconceptions or preferences. He describes the current situation as a learning experience and a work in progress, noting that curiosity and humility to learn from new data define the scientific process. This approach stands in contrast to assuming that past knowledge can fully predict what nature will reveal, particularly when dealing with objects from outside our solar system that may have experienced very different formation conditions. The scientific method demands that all hypotheses remain on the table until evidence definitively rules them out. In the case of 3I Atlas, this means considering both natural and artificial explanations, while gathering the observational data needed to distinguish between them. Each new image and spectrum provides additional constraints on the possible mechanisms producing the observed phenomena. The accumulation of evidence over time will eventually point toward one explanation or another. Loeb also draws a distinction between the foundation of science, which he describes as curiosity and humility, and what he calls the arrogance of expertise. This arrogance assumes that past knowledge can forecast what nature will reveal. With interstellar objects, this distinction becomes particularly important since these visitors formed in alien stellar systems under potentially very different conditions than objects in our own solar system. The possibility of 3I Atlas being technological remains unconfirmed and represents one hypothesis among others being investigated. Loeb notes that if the object proves to be natural, there's nothing to worry about regarding Earth's safety. He suggests not losing sleep over the matter until more definitive evidence emerges about the object's true nature. His comment about hoping for no gifts from this object for the holidays reflects a light-hearted acknowledgement of the uncertainty while maintaining scientific objectivity. Current observations cannot yet distinguish definitively between the fragmentation scenario and the thruster hypothesis. Both remain possible interpretations of the data pending higher resolution, imaging, and spectroscopic analysis. The resolution of ground-based telescopes and current space imagery hasn't been sufficient to identify individual fragments if they exist, nor to measure jet velocities with the precision needed to distinguish natural from artificial origins. The technical challenges of observing 3I Atlas include its relatively small size, its distance from Earth, and the need to track a fast-moving object against the background stars. Advanced adaptive optic systems on ground-based telescopes help compensate for atmospheric distortion, while space telescopes avoid this issue entirely but have limited observing time available. Coordinating observations across multiple facilities maximizes the chances of capturing 3I Atlas during moments of unusual activity. The 7 or more jets visible in the latest images show tight collimation, meaning they maintain narrow, focused streams rather than dispersing rapidly, as might be expected from simple gas expansion into vacuum. This collimation extends over vast distances, with some jets reaching 1 million kilometers from the nucleus. Such extended, narrow jet structures require either continuous outgassing from specific surface locations with unusual geometries or directed propulsion, maintaining the flow against the natural tendency of gas to expand in all directions. Natural jets from comets typically form when subsurface volatile pockets become exposed to solar heating. The geometry of these pockets and the surrounding terrain can create nozzle-like structures that partially collimate the escaping gas. However, maintaining collimation over 1 million kilometers requires special circumstances, such as electromagnetic effects on ionized particles or continuous acceleration from an active source. The observed collimation in 3I Atlas's jets exceeds what most cometry models would predict. the comparison between natural cometary processes and potential artificial mechanisms extends beyond just ejection speeds. Natural outgassing typically shows correlation with solar distance and illumination patterns, increasing as the object approaches the Sun and decreasing as it recedes. The distribution of jets around the nucleus usually reflects the spin state of the object and the location of volatile deposits. Artificial thrusters might show different patterns, potentially oriented for trajectory modification rather than following thermal gradients. As 3I Atlas continues its passage through the inner solar system, each day brings new opportunities for observation using different techniques. Multiple telescopes monitor the object continuously across various wavelengths, from radio through infrared to visible light and ultraviolet. This multi-wavelength approach helps identify the composition of ejected material and measure temperatures, velocities and densities within the jets. Spectroscopic observations provide particularly valuable information about the jet's composition. Different molecules and atoms emit and absorb light at characteristic wavelengths, creating spectral signatures that reveal what materials are present. Comparing these signatures with laboratory measurements and theoretical models helps determine whether the jets contain typical cometary volatiles or something unexpected. The presence or absence of specific molecules can confirm or rule out certain formation scenarios. Radio observations can detect emissions from various molecules in the jets, including water, carbon monoxide, methanol, and other organic compounds commonly found in comets. Infrared observations reveal thermal emission from dust particles and can measure their temperatures and sizes. Visible light observations track the overall morphology and evolution of the jets over time. Ultraviolet observations can detect emissions from atoms and simple molecules excited by solar radiation.